SBIR has developed a novel approach to vectorize video, sonar, radar, and other hyperspectral data using mathematical models called Bézier curves. We like to start with this Van Gogh self-portrait because uniquely among all artists, Van Gogh painted in brushstrokes that look like Bézier curves. And this image illustrates the ability of our shape-based approach to find all of his strokes in this self-portrait. More importantly, there are some significant implications about each of those strokes. Uh, we know where each of them are. We know what their length is, their radius of curvature and orientation. And it's worth mentioning and keeping in mind as we move through this presentation that vectorization in the computer industry has been around for a long time. But people like Google and Adobe tend to use vectorization for scaling, making sure graphics display consistently on different types of mobile screens. But Vi is developing vectorization primarily for object identification and robotics. And our big differentiator is the ability to recover objects and areas of interest from noisy background. Vi is bringing state-of-the-art vectorization solutions to make decisions about objects and areas of interest in environments with noise and occlusions. We're an artificial intelligence software company, and we've developed and patented a platform to vectorize and make decisions about big data, typically data that's generated by satellites, video, radar, and sonar. And our performance criteria are really looking at use cases involving superhuman performance with no training, auditable and transparent decision making, and faster and more reliable recognition. We call this shape-based modeling because it uses mathematical models called Bézier curves and decision trees to vectorize data at multiple thresholds and resolutions. This approach is game-changing and disruptive because it turns pixels into scale and angle invariant mathematical functions. And our real competitive differentiator versus conventional techniques is the ability to query that novel vectorized data in an industry standard database using industry standard tools like Python, QGIS, and others. It's a disruptive package, which we've positioned as a cloud-based offering using SaaS, and we call this ARES, Abstraction, Reasoning, Interpretation, and Extrapolation Suite. And we're targeting three primary verticals, the military and government space, commercial, satellite image analysis, and life sciences. Vi is a 10-person small business headquartered in suburban Philadelphia. We've assembled what we think is an ideal team to scale our shape detection technology. Our CEO, John Freihoff, is a successful entrepreneur and capital markets professional, having funded and successfully exited from 14 different companies. Our CTO and co-founder, Tom Martell, is an electrical engineer. He's also the inventor of the technology. Tom is a General Electric A course graduate, and prior to joining Vi, ran a successful electronics small business for a number of years. In addition to the commercial and university partnering opportunities and relationships you see mentioned on this slide, we also think it's important to note that as part of our recently completed Navy Accelerated Phase 2 project, we had one large prime and two successful small businesses serve as subcontractors. And from our perspective, the existing relationships that are ongoing and some of the ones we're moving into have important implications for our ability to scale this technology. Vi was tasked by the Navy with a dual-use project to develop a new automated target recognition approach for identifying subsurface threats, and also to investigate the ability of our technology to do signal source separation using marine mammal data. Our phase 2 results achieved surprising results in the sense that we achieved accuracy rates from 75 to 100% in three different bottom conditions: relatively easy sand ripples, hard smooth conditions, but also complex bottom conditions. And in the areas of Bézier enhanced deep learning, which we're showing in the lower right quadrant of this slide, we're achieving convergence rates of 50 to 100 times faster with as little as one training vector versus conventional deep learning alone, which can require thousands and in many cases millions of training vectors. More importantly, and a significant implication of this work is that as magnification increases from 1x to 2x, our results improve dramatically. This slide shows the shape technology that's under the hood, so to speak. We've developed a platform to find Bézier curves at multiple resolutions and multiple thresholds. They're scale and angle invariant. They can reliably handle occluded objects, and they can also be linked together to reliably find convex objects, whether they're occluded or not, with no calibration. The test image on the lower left-hand side of this slide is an example of what we call a senior Bézier curve that's spatially associated with several lower resolution curves. And why is that important? It's important and game-changing because those relationships provide auditable data to confirm or support evidence of an object that's real based on those reporting relationships. And we're showing in the upper right-hand side of this slide how this methodology can be used to tackle a real-world problem, occlusions in a noisy real-world environment using synthetic aperture radar. We're showing in the upper right how the problem of speckle noise with SAR can be addressed. And in the lower right, we're showing that this methodology can reliably find ships, and more importantly, provide a layer of data that could be corroborated or correlated with other available data sources like AIS. It's transparent, it's auditable, and from our perspective, it's game-changing. This slide summarizes three critical areas where ARES, our shape modeling technology, can provide game-changing capabilities for autonomous vehicles. There's a real need to allow unmanned underwater vehicles to operate with full autonomy. Today, these platforms have limited communication with the surface, and they've traditionally used simple pre-programmed tasks and telepresence to complete their mission. It's important to understand as part of this that what a computer sees and what a person sees are very different. The customers we're targeting here are typically using artificial intelligence tools to curate subsurface information, but they're doing that with varying degrees of success. The bottom line is that there's an element of unpredictability with most AI systems. They tend to be very good at learning, but they're not very good at abstraction. Things like changes in lighting and angles can cause unexpected decisions. Our ARES vectorization topology is very good at abstraction, and it's ideally positioned to bridge that unpredictability gap. And we're targeting three areas, as this slide shows: maneuver operations, onboard processing, and situational awareness. This slide summarizes a novel approach for signal source separation using adaptive filtering by frequency domain vectorization. Working with unclassified marine mammal and ship signal data from a study conducted at the Unimac Pass back in 2016, we were able to prototype a methodology for superhuman performance for signal separation. What we're showing in the upper left-hand quadrant here is the raw signal. The upper right shows how we're expanding that signal for submission to our Bézier transform using fixed Fourier transforms. And then in the lower left quadrant, we're showing how meta-Béziers fitted to the orderly parts of those signals are eliminating virtually all of the noise. In the lower right, we're describing a novel new approach for recovering signals from a noisy background that facilitates superhuman performance capabilities. SBIR has developed a novel new way of turning the function of isolating marine mammal sounds from the background into a signal processing architecture that's very much like an FM receiver. And if you look at notes B1 and B2 in that lower right quadrant, you'll note that that indicates two distinct whales. Our scientific expert was only able to detect one of those whales because the second call was buried in the noise of the first. Because of this capability, we call this initiative Project Jonesy, in honor of the famous operator from the movie The Hunt for Red October. The second of three key areas we'd like to focus on today is the ability to identify subsurface threats using ARES vectorization. Current technologies are very good at finding subsurface threats in sandy bottom conditions, but there's a significant gap in finding threats as they progress into hard and more complex bottom conditions. Here we're showing a framework to develop a series of auditable Boolean rules to find and characterize subsurface threats. The upper left quadrant here is showing the native image of a possible threat. The upper right showing the classification rules that we're using. And the lower left is actually showing the candidate curves based on the meta-Bézier corroboration that we covered earlier. And finally, in the lower quadrant, we're showing the actual target. The significance is that we're dealing here with potential occlusions, cluttered background, and varying bottom conditions. And the system, because it is audible and transparent, is able to perform very well and has a built-in feedback loop to correct problems as they arise. The third use case we'd like to present today is showing how the same technology we presented in the prior slide to look for subsurface threats can actually be used for automated labeling. In this case, we're looking at satellite imagery to find and use geoencoding to identify buildings and houses. Working with a world-class team at the University of Pennsylvania, we've prototyped a methodology to significantly improve convergence and reliability in conventional deep learning systems with fewer training vectors, basically by adding Bézier shape layers to that conventional process. We'd mentioned that on an earlier slide, how we were getting 50 to 100x improvements in convergence. And this is another demonstration of how we were able to do that with some additional test data using some COCO data set. This is a schematic showing how the Bézier enhanced deep learning we showed on the prior slide in terms of the airplane results is working with both existing and next generation deep learning systems to achieve that 50 to 100x convergent rate improvement that we talked about. The work is ongoing, but the significance is that we're now working with 3 large primes to introduce this approach on commercial cloud platforms. We've packaged our solution in a scalable Docker container called Aries, Abstraction, Reasoning, Interpretation, and Extrapolation Suite. It can be delivered on a commercial cloud platform, a secure government platform, or it can be run standalone. Pricing is tied to usage, and we also have a model where we can license module to perform custom development and meet certain customer requirements. Our processing time using this approach is currently about 30 microseconds per pixel per core with a 3 gigahertz processor. We have an aggressive transition plan in place, and in addition to working with the Navy and the Air Force, we're currently working with 5 large primes to transition our technology for both government and commercial use cases. On the military side, we're targeting anti-submarine warfare, automated target recognition, and autonomous behavior. On the government side, we're focusing primarily on satellite image analysis and geospatial use cases. And in the commercial sector, we're looking at weather, utility vegetation management, and insurance underwriting verticals. In addition to the 3 areas we've identified in this presentation, subsurface threats, source signal separation, and automated labeling, there are a number of potential growth areas where this technology can be extended. Fully autonomous maintenance and construction for deep sea and space use cases, 3D modeling and analysis, and node network programming for domain experts. There are 3 significant takeaways from this presentation. First, there's a desperate need for fully autonomous behavior in current and future UAS UUV platforms. Secondly, our Aries, Abstraction, Reasoning, Interpretation, and Extrapolation Suite is ideally positioned to fill the gap to meet those needs. And finally, the solution we're talking about is operational today. It can be integrated with existing systems or run standalone. And we're seeking additional prime vendor and Navy partners to help us implement this technology. And we would love to have you contact us with questions, comments, or follow-up based on the contact information on this slide. Thank you.